Hi everyone, so this is 3.1, derivatives of polynomials and exponential functions. And the first one we want to recall is the derivative definition, which says that f prime of x is equal to this limit. And we're going to apply it to prove general rules. Now the first one is a legitimate rule, constant rule, derivative of any constant. So like we can find derivative of, let's say, 2 or 3 or 1/2 or any constant. This is derivative of x, and we'll generalize this into derivative of any power of x. But before telling you what the result is, I want to show what it is by proving it, basically, by using the definition. So let's see. So we say that this derivative, where the function is c, that's what we're taking derivative of anyways, f prime of x is equal to limit as h goes to 0 of what? Well, it's all over h. On top we have something minus something else. It's f of x plus h. Since f of x is c, f of x plus h is going to also be c. And then f of x will again be c. Okay, so far so good? So c minus c over h, that's just 0 over h. And 0 over anything is 0. Even as h goes to 0, the result will approach 0. So the constant rule tells us that derivative of any constant is just 0. Which I think makes sense, because if you think about how you graph any constant, it's just going to be a horizontal line. So this is the line y equals c, or if you like, f of x equals c. And notice, any point you pick, its derivative will just be the slope of the line itself. Since it's horizontal, its slope is 0. So it makes sense the derivative of any constant will also be 0 for that same reason. Okay, the next thing is, what's the derivative of x? Well, with this in mind, if you were to graph y equals x, the slope is 1. And picking any point on the line, the tangent line is just the line itself. So the slope should be 1 as well. And in fact it is 1, and I'll prove it using this. So if f of x is x, then f prime of x is the limit as h goes to 0 of all over h f of x plus h. F of x plus h is just, well, x plus h in this case, minus x, which is f of x itself. Notice the x's cancel, so we get h over h. This is limit as h goes to 0 of h over h. But since h over h reduces to 1, this is just the limit as h goes to 0 of 1, which would itself be 1. So that proves this rule. For derivative of x, the derivative is just 1. So a lot of things we'll be doing in this section. Mainly we'll be doing what we've just done here, finding different rules for certain things, and we'll see a few more right now. Alright, so the next thing now to discuss is the constant multiple rule and the addition rule. By the way, these are two properties known as linear properties. Basically, if you can pull a constant out of an operator and the operator applied to two things added together is the same as applying that operation to each of them term by term, so derivative of the sum is the sum of the derivatives, then the operator is known as what is called linear, and the derivative is a linear operator, as it turns out. Which is kind of a deep concept somewhat, but just kind of know that. You don't have to know that, but know that. So I'm going to prove these. So first off, for derivative of c times f of x, well, if our function is, so it's going to be a little hard to look at, but if our function, let's call it capital F of x, is equal to c times f of x, then capital F prime of x is equal to what? It's equal to the limit as h goes to 0 of all over h f of x plus c, which is c times f of x plus c. I meant x plus h. My mistake. Minus capital F of x, which is just c minus f of x. Alright, so now what? Well, there are a few properties we can apply here. The first big one is that c is what the top two both have in common. So we can pull c out. In fact, that constant multiple will not affect the limit, as it turns out. So what we can do actually is pull c out of the entire limit. So c times the limit as h goes to 0 of all over h, the top without the c's, which is just f of x plus h minus f of x. And if you don't recall, what does this look like? What does it remind you of? It's just f prime of x. And that proves it, because now we can say that this is just c times f prime of x, and that completes the proof. So we can box this and throw this on our list of rules. And now on to the next one. It's going to be fairly similar. We're going to call capital F of x equal to f of x plus g of x. And then we're going to attempt to find capital F prime of x using the definition of derivative. So it's limit as h goes to 0 of all over h f of x plus h, which is just f of x plus h plus g of x plus h. Maybe I should have called it h of x instead of capital F of x. No, h of x would be terrible because we're already using h, aren't we? That's fine. So that minus original capital F of x, which is just f of x plus h, but since we're subtracting the whole thing, just to save space and I guess time, I'm going to imagine distributing the negative into f of x plus g of x. We'll get negative f of x minus g of x. Whew, nice. And now the last thing to do is to split this up and rearrange it. And there's a limit property that allows us to pass things through the limit as follows. So we can write this as the limit as h goes to 0 of, so I'm going to pull this apart in a particular way. I'm going to do the f's in one fraction. So f of x plus h minus f of x plus the g's in the other fraction. So all over h. So that's going to be g of x plus h minus g of x. And I did say that we can actually use a limit property that allows us to say the limit of the sum is the sum of the limits. Basically, adding two things as long as the limits exist doesn't affect the limit. So there we go. And what do you notice again? This is nothing but f prime of x. And this is nothing but g prime of x. These are just each the definition of derivative for each f and g as functions. So this is just equal to f prime of x plus g prime of x. And there we go. We have proven the addition rule. Great. So now we've proven these rules, and we're going to take a look at a few more. And then we can actually do some examples using these ideas. Alright, so now for the granddaddy of all the rules in 3.1, the power rule. And the power rule says the derivative of any power of x can be written as n times x to the n minus 1, meaning you drop the power down and then decrease the power by 1. Okay? And this works for any real number n, so this means n is a real number. But I'm only going to prove it for n being in the natural numbers, meaning positive integers 1, 2, 3, and so on. The reason why I'm only going to prove it for these is because to prove for every real number is a little involved, so I'll just prove it for positive integers, and you'll just take my word for it that it's true for all real numbers, but we'll eventually see the proof for all real numbers, but we don't quite have the tools for that yet. Now, in order to begin this proof, I first need us to recall binomial theorem. Kind of binomial theorem. I'm not going to write out binomial theorem exactly, but I'll at least say what part of binomial theorem says, at least for what we need. And we need this. So in the context of what we're trying to prove, we want to expand out x plus h to the n. And you'll see that this comes from the difference quotient, so that's why we need this. And to expand this out, the binomial theorem basically tells us that this is x to the n plus n x to the n minus 1 plus h times some polynomial. that's basically all we need. And yeah, so the binomial theorem says something more specific, but I'm going to use kind of this version of the binomial theorem, if you will. Okay, good. So after recalling that, let's actually begin the proof now. So if f of x is x to the n, then this implies that, well, f prime of x, the derivative of x to the n, is the limit as h goes to 0 of all over h, x plus h to the n minus x to the n. And now first notice x plus h all to the n is this, from what we recalled from binomial theorem. So we can write it as just replacing it with that. Limit as h goes to 0, we have h on top, or h on the bottom. On the top we have x to the n plus n x to the n minus 1 times h. I forgot to write h here. And in fact, you know what? This should have been plus h, and then that's actually, they all have h squared in common. Essentially what the binomial theorem says is that as powers of x's decrease from n to 0, powers of h's in each term will increase from 0 to n. So 0 h's, 1 h, 2 h's, 3 h's. So everything here beyond will have at least 2 h's in common. So sorry about my mistake on that, but let's continue. So times h plus h squared times some polynomial. Okay? And minus x to the n. So notice what we always want to happen happens. Everything except for things involving h cancel out. So then we can pull h out from the top. Pulling h out from the top from what's left over, we have, well, this without the h, so that's n x to the n minus 1, plus pulling an h from this leaves you 1h still, multiplied by this polynomial. Okay? All over h, the h's finally cancel. Then, taking the limit as h goes to 0, well, this guy is going to approach 0 in the limit. So all we're left with really is this, which is exactly what we were trying to prove. So now I'm going to prove one last rule for you, and then we can move on to do some examples finally. Alright, so this next and final rule is a really cool one. It's the natural exponential rule. It basically says that the derivative of e to the x is itself, and as it turns out, it's basically the only function that has that property. This is also a little bit out of our control to prove right now. We don't quite have the tools for it yet, but we will prove it eventually using something greater that Chapter 3 basically builds up to, kind of. But right now, I'll just give you this fact, and with this fact, we can prove it. So this fact itself is kind of hard to prove at this level, but you can take my word for it, or you can actually use your calculator. I showed you this before. This is one way you can convince yourself that some limit is true. Plug in something very close to what we're trying to approach. So here I'm going to say that this fact says limit as h goes to 0 of e to the h minus 1 all over h is equal to 1. And you can check by plugging something in your calculator that's extremely close to 0, let's say 0.001. So in your calculator you can do e to the 0.001 minus 1 over 0.001, and this should approximately give you 1. And the closer that these numbers, they have to be the same number, the closer they are to 0, the closer this value should be to 1. You can even graph this if you like, but believe me, this works out fine. So you can kind of, I guess, that should be a quotation check like that, because that's not entirely how you check limits, but it's one way you can convince yourself anyways. Okay, so now, yeah, let's try to use this in our proof. So if f of x is e to the x, then what's f prime of x? Well, again, using our definition of limit, by the way, this is basically going to be the last time we're using the definition of derivative. After this, it's all shortcuts. It's the limit as h goes to 0 of all over h, f of x plus h, which is e to the x plus h, minus f of x, which is e to the x. And there's a few things you can do. You can rewrite the first term as e to the x times e to the h. Since you have the same base, you can add the powers and you'll get exactly this. Also notice e to the x is the same as e to the x times 1. So what I'm basically trying to say is what we can pull out from the top is just e to the x itself. Because they both, of course, have e to the x in common. And, just like we saw from the previous proof, a property we use anyways, we can pull this common factor so long as it's independent of what we're approaching, the variable that's approaching 0, h. E to the x is independent of h. We can pull that out of the limit. So this altogether is e to the x times the limit as h goes to 0 of what's left over. This without the e to the x's is e to the h minus 1 all over h. And what do we just see in this fact? This is 1. So in the limit, this whole thing is equal to e to the x times 1, which is just itself e to the x. Perfect. Finally, we finished proving all the cool rules from 3.1. Now finally, let's see some really awesome examples. Okay, so here are some nice 6 examples that we can do all on one board, basically. I believe we can anyway. So that's kind of the power of all these rules that we've just witnessed and we've proven, which is great. There are some that require a little bit of setup, but for the most part, they're good to go. So here, I'm going to just start right away. Jumping into derivative, there's no setup, there's no steps. Just applying the rules. That's all we do. So remember, the addition rule says we can take derivative term by term. So let's just do that. Derivative of x to the third is 3x squared. Remember how we do that? Bring the power down. The new power is 1 less than the previous power. Derivative of x is 1. And derivative of negative 4 times x is negative 4 times 1, which is just negative 4. So that was using the constant multiple rule. Basically, we just don't care about constants. Constants come down for free, as long as they're multiplied by something. 6 as a constant on its own, and we had a rule for that, its derivative is 0. So I could write plus 0 if I wanted to, but I'm not even going to write that. Adding 0 does nothing, so that's it. This is the answer. If we had used a definition of derivative, it would have taken like practically the whole board, and it would have taken a lot of time as well. Okay, moving on to number 2. There's some setup here, and let me write, I guess I can write it here below. This is x to the 1/3 minus 3, radical x is x to the 1/2. So this is something that you should know from algebra, and let me write it here in blue, I guess. If you have the nth root of x to the m, you can always write this as a power as x to the m over n. The thing to remember is that the denominator is the root, like here this is the root of the radical, where this is the actual power of x on the inside. And you can actually interchange these, so you can actually write this as the nth root of x to the m, or the nth root of x all to the m. But in any event, we're using that to write as a power of x, and now we can apply the power rule. Term by term, remember that? So now derivative of x to the 1/3 is 1/3 x to the, what's 1/3 minus 1? Well, 1 minus 1/3 is 2/3, so 1/3 minus 1 is negative 2/3. And there's actually a few ways you can see that. Basically, if you write 1/3 minus 1, you can find a common denominator and combine them to negative 2/3. But there's a quick trick I want to show you. If you want to subtract 1 or take 1 away from a fraction, you can always do the following. Top minus bottom, all over the same denominator. So in this case, look, what's 1 minus 3? It's negative 2 over the same denominator, 3. So now let's try that trick for the next one. The only thing is, we need to bring 1/2 down. So I'm going to multiply 1/2 to the number in front, negative 3. Negative 3 times 1/2 is, you guessed it, negative 3 over 2. Because 3 over 1 times 1 over 2 is 3 over 2. Multiply straight across. X to the, let's see if we can do it. Top minus bottom. 1 minus 2 is negative 1 all over 2. So that's the new power. And I would be honestly okay for you writing your answer like this, but we can rewrite it in terms of radicals. The fact that they're negative, though, we write them on the bottom. And that's another rule from algebra that we probably don't have space to write. But let me just show it to you as our final answer here. Squeeze it in. So f prime of x is 1 over 3 times the cube root of x squared minus 3 over 2 times the square root of x. Okay, to squeeze that in a little bit, let me try to explain. So first off, the negative powers mean that they're actually in the denominator. Hence why 1 stays on top, 3 only stays on top. Okay. Secondly, remember x to the 2 over 3 means the cube root of x to the 2. So there's that, but in the bottom because it was negative. Similarly, x to the 1/2 means radical x, but again, since it was negative, we write radical x in the bottom, multiplied by that 2 that's already in the bottom. Like this radical here was multiplied to this 3 that was already in the bottom. So I'm skipping some details, but there's that. Okay, for this one, there's also some setup you have to do. You have to split this up. So f of x is x to the 4th over 4x squared plus 2x over 4x squared. After splitting it up, you can reduce each one of them. So this is actually 1/4. So I'm pulling the constant off to the side. 1 over 4 is the constant. X to the 4th over x to the 2 is x to the top power minus bottom power, which is x to the 4 minus 2. That's just 2. Similarly for this one, pulling the constant off to the side, 2 over 4 is 1 over 2. And x to the 1 over x to the 2 is x to the 1 minus 2, or x to the negative 1. Good. So now applying the power rule, okay, you bring the power down, so this is now 2 over 4, because you multiplied 2 over 1 to 1 over 4, so it's 2 over 4, times x to the 2 minus 1, which is just x to the 1. Minus, because negative 1 comes down, negative 1 multiplied to 1/2 is negative 1/2, x to the negative 2, because, well, negative 1 minus 1 is negative 2. So then finally here, what do we get? Well, I'm going to rewrite this a little differently. So 2 over 4, first off, is 1/2. So it's 1/2 x. X to the 1 is just x. Minus 1 over 2x squared. And I hope you can see how I got that. I'm just basically bringing x to the negative 2 down to the bottom as x to the positive 2, joining in that 2 that's already there. Okay? Similar to what I did for part 2. Okay, part 3 is going to be pretty similar, and part 6, part 5 is okay. Part 6, we probably don't have space for, but it's basically this. It's all squeezed together. Sorry about that. But let's see. So derivative of, let's see if we could jump to it. Well, we can't quite jump to it, can we? We could jump to it for these two. These two are okay, but the middle one you need to rewrite as, let me do it here, negative 3x to the negative 3. Hope we can see that okay. Negative x3 to the negative 3. Okay, so now that we have that settled, the derivative then is what? Well, bring the 3 down, so it's 12x to the 2, because 3 minus 1 is 2. Again, you subtract 1 from the power. Minus, well, actually not minus, because look, this negative 3 power comes down and multiplies by that negative 3 that's already there. So it's positive 9x to the negative 4. And then, so let me kind of erase this. And then finally, the last term, the derivative of 5 times e to the x is 5 times derivative of e to the x, which is just itself 5e to the x. And that's it. Again, you can write this as 9 over x to the 4 if you like. So I'm going to write that in blue, writing this as 9 over x to the 4. So if you want to write it with no negative powers, it's as simple as that. On to 5 now. Part 5 says f of x is equal to e squared plus 2 to the 3rd minus x. So what is the derivative of, remember, term by term. So what is the derivative of e squared? Well, derivative of e to the x is itself, right? So the derivative of this would be e squared? No, not quite right. If it's e to the x, then its derivative is e to the x. Since e is a number, I didn't mention this earlier, but e is a number, it's a constant. It always has this value, 2.71828. Kind of like how pi always has the value 3.14. The only issue is that it's just represented by a letter, And we often forget what that represents, but don't forget this represents this number. And your calculator knows it if you forget it. There's a button for it on your calculator. So with that being said, since e is a constant, e squared is also some number. And what's the derivative of any number? It's 0. So the first term is 0. Secondly, for the second term, 2 to the third, you don't apply the power rule. If it was x to the third, then it's 3x squared, yeah. But if it's 2 to the third is just 8, which is a number, similarly to how e squared was a number, and its derivative also is 0, because there were no x's involved. That's the big point. The biggest point here is that if they don't have x's involved, chances are they're constants and their derivatives are 0. Okay, moving on. Derivative of x is 1, so this is negative 1. So in total, the derivative of f of x is just negative 1. Now notice when I have space, I try to include f prime of x in my answer. I didn't for part 3, but I did for all the other ones. I just didn't have space. Let's see if we have room to do this one. I believe we don't. Just to play it safe, I'm going to erase and write it right now. By continuing part 6, like I said, this requires a little bit of setup. We can split it up like we did one of the other ones. The only thing though is that I'm also going to rewrite the radical as a 1/2 power. And that's pretty common in this class. We'll be doing that a lot actually. So I'm going to not only split it up as t squared over the common denominator, 4t over the common denominator, and then plus 3 over the common denominator, but I'm simultaneously going to replace radical t with t to the 1/2. Then I'm going to subtract the powers. Okay, so this is t squared over t to the 1/2, so that's t to the 2 minus 1/2, plus 4t to the 1 minus 1/2, plus 3t straight up to the negative 1/2, because that's how you take advantage of negative powers here. If you have a power on the bottom and you want to bring it up to the top, bring it as a negative. Another way to see this is that anything to the 0 is 1, so you can always throw in an imaginary t to the 0 because anything times 1 is itself. And then top power minus bottom power is just 0 minus 1/2, which is 1/2 as a power. Good. The only thing now I guess we have to do is just combine these. So 2 minus 1/2 is 1.5, which is 3/2. 1 minus 1/2 is 1/2. And that's still negative 1/2. The other thing to remember is this is not derivative. We're not finding derivative yet. We're just setting it up so each of our terms are powers of the variable so we can apply the power rule. So this is still f of t, not f prime of t yet. And notice how the variable isn't x here like we're used to, it's t now. So be wary of that. So now, f prime of t is, applying the power rule, 3/2 t to the 3/2 minus 1 is just 1/2. Remember the trick. Top minus bottom, so 3 minus 2 is 1 over 2. Okay. I was going to write plus. It is still this plus actually. So 1/2 comes down. 1/2 times 4 is 4 over 2, which is just 2. T to the 1 minus 2 is negative 1 over 2. This one is the one that becomes negative. Because 3 times negative 1/2 is negative 3 over 2. So bringing the negative 1/2 down, 3 times negative 1/2 is just negative 3 over 2. T to what power? Well, remember it's top minus bottom. Negative 1 minus 2 is negative 3 over 2. And now we're really done. All we really need to do, I guess, is combine these and rewrite them as fractions, as rewrite them as non-negative fraction powers. I kind of don't want to do it, but we can. You can write this as 3 radical t over 2 plus 2 over radical t. Let me do that again. There we go. And I think we see how I got these first two. It's not too bad. This next one I want to talk a little bit about. So it's going to be minus 3 over 2 times. You're probably going to expect me to write the square root of t cubed. And I would, except the square root of t cubed can actually be simplified. Here's something you can recall for yourself. The square root of t cubed is the square root of t squared times t. If you split this radical up, it's the square root of t squared times the square root of t. The square root of t squared cancels out the radical and you just get t on the outside of the radical times t inside the radical. So it's just t rad t. So I'm actually going to replace this right away with t rad t just to save space. And now, I didn't do this in any of the other examples, but we could have if we wanted to. Let's find a common denominator. So I'm going to multiply top and bottom of the middle term by 2t. And the first term, top and bottom, by just t radical t. That'll get us a common denominator. Also notice, radical t times radical t is just t. Since we already have a t on the outside, it's going to be t times t, which is t squared. So altogether, finally, we'll have f prime of t is equal to 3t squared plus 4t minus 3 all over 2t radical t. I was going to leave it at this as far as being the last example, but there's one more example that we deserve to see, and let's see that right now. Okay, so this is the last problem for this video. Here I asked to find an equation of the tangent line to the curve at the given point. So the curve is going to be, well, it's going to have the equation y is equal to this, x to the 4 plus 2x squared minus x, and the point is going to be 1, 2. One thing to notice is that if this is indeed a point on this curve, then plugging in this x value should give this y value. And we can just assure ourselves of that. 1 to the 4th plus 2 times 1 squared minus 1 is 1 plus 2 minus 1. The 1's cancel and we indeed get 2. Great. All right, so now what we're going to do is find the equation of the tangent line at that point. Now, of course, to find the equation of a line, we need two things. First, we need to find the slope. Then we need to find the equation using point slope. So the first step is to find the slope. What is the slope of the tangent line? The slope of the tangent line is, well, it is the derivative of the function, so dy dx. That's our Leibniz notation if we remember that. Evaluated at x is equal to whatever the x value of the point was, which is 1. So I don't know if I've quite shown this notation, but this just means evaluated at. Another way of phrasing this, honestly, is f prime of the x value, f prime of 1. So if our y, if we call our y f of x, then this is another notation for that. So to do this, let's first find, so just to recall what this is f prime of x evaluated at x equals 1. There's that evaluated line again. Just to remind us what we're doing. First, we're finding the derivative of f, then we're plugging in x equals 1. So what is f prime of x? F prime of x, just use the power rule in each term. So that's going to be 4x to the third plus 4x to the 1, or just 4x, minus 1. So if you follow taking derivative of each of these, you'll get this. Then, plugging in 1, we'll get that f prime of 1 is equal to, plug in 1 for x, 4 times 1 to the third is just 4, plus 4 times 1 is just 4 also, and then minus 1. So that's 8 minus 1, so the slope is 7. Perfect. Now we can use point slope. So let us recall, point slope says y minus a y value of a point is equal to m, the slope of the line, times x minus the x value of the point. And here our point is this. It's 1, 2. So all we have to do now is let x1 be 1, y1 be 2, m is 7, plug those in, there it is. All we have to do now is solve for y and we're done. So distributing the 7, we get y minus 2 is equal to 7x minus 7, adding 2 to the other side, and finally, we get the equation of the tangent line. Y is equal to 7x minus 5. Perfect. Now, a really cool thing you can do here is you can actually graph these. On your graphing calculator, you can press y equals, type this in to get this curve. It's going to be some polynomial looking thing. It may look something like a W. Something like that, perhaps, is maybe what it looks like, just by looking at it. So it kind of looks like a W, I guess. And then if you graph this, then you'll see at the point 1 comma 2, let's just say, for example, this is the point 1 comma 2, that line should give you the tangent line at that point. Now this is of course just a sketch. This is nowhere near looking how this is going to look. And I know that because 7 as a slope is a pretty steep slope. You go up 7 over 1, imagine how steep that would be. And here I'm not making it look steep, of course, but that's the idea. And if you graph them, you'll get that exact image. That concludes 3.1. Hope you all enjoyed it. It was really, really fun. We're going to have more fun in the next sections, and I'll see you then.